So where things stand are, I'm trying to explain to you how power is moved across only the country, across the neighborhood, into your house, how electric power does that. It involves multiple circuits and moving energy from circuit to circuit because of these issues of voltage and current. High voltages are great for delivering power efficiently because they involve sending relatively little current through wires, and wires waste energy according to the current that flows through them. So back off on the current. How do you do that? Crank up the voltage. But you can't deliver at high voltage because it's too dangerous. So you have to shift gradually to lower and lower voltages and higher currents to deliver the power. And associated with this, and I'll go over this view graph, and then I'm going to go through a series of demonstrations, really, of things that I have left behind or not gotten clear, or maybe it's time to revisit them anyway. But the point of this view graph then is to sort of finish fleshing out the relationships, actually with one left, between electricity and magnetism. And I've got ways to show you a bunch of these ones. Way back when, the story seemed to be that electric charges exert forces on one another. They're the only thing, it seemed, that was responsible for electric fields. I mean, why even have electric fields at all? It's just about these charges, okay? And the world of magnetism seemed very simple. It's just magnetic poles, and the only thing that seemed to be able to create a magnetic field was those magnetic poles. In reality, no, they're all intermixed, and there are multiple ways to make electric and to make magnetic fields. And so this is my little summary slide. We got one last entry to come up, just to go through it again. To produce a magnetic field, yeah, a magnetic pole will do it. Magnetic poles create, a north pole has a magnetic field pointing away from it, and a south pole has a magnetic field pointing toward it. Subatomic particles often carry with them magnetic fields. They have the magnetic poles and therefore create magnetic fields. But it turns out those are not the only things that can create magnetic fields. Moving electric charge does it too. So if you have electric charges heading off to the right, typically inside a wire as an electric current, that's magnetic. Okay? It creates a magnetic field. It will therefore push on magnetic poles. The last one here, and I'll tell you about it anyway, because we are working our way towards radio, which is the next topic, which I might get started in today. We'll see. It turns out that you can also make magnetic fields by having an electric field that changes with time. So if you have, well, let's see. Oh, the electric power company. Remember, the electric power company has this strange thing where the voltage of the power slot in the outlet, that voltage goes up and down from high voltage to low voltage, high voltage to low voltage, in fact, to negative voltage, up and down. If you take those two wires out, the neutral and power, neutral is at 0 volts, ideally. The voltage of power goes to high positive voltage to low negative voltage and back and forth. The electric field between the two wires is changing with time. There's an electric field, after all, whenever there's a gradient in voltage. And there is a gradient in voltage. You've got 100 volts here on the power wire at this moment in time, and 0 at the neutral wire. And a little while later, this is different in voltage. So between the two, there's a gradient in voltage. So therefore, there's an electric field. And that electric field is changing with time. You follow that idea so far? Amazingly enough, there will be a magnetic field produced by that changing electric field. Okay? Who knew? That was a deduction that was made during the wrapping up of the whole idea of a radio wave. Like, it has to be there, and it's there. Okay? It was more predicted than it was observed. So magnetic fields, there are a couple ways to make them. How about electric fields? Well, there was the original way of making it, just have electric charges around. And it turns out that electric charges come for free on certain subatomic particles. So you got them. So certain subatomic particles have electric fields around them. An electron, for example, or a proton that is the nucleus of hydrogen, the hydrogen atom. Okay, but there are other ways of making electric fields. And one of them is a moving magnetic pole. It's very symmetric with a moving electric charge creating a magnetic field. If you have a moving electric charge, there's a magnetic field around it. If you have a moving magnetic pole, there's an electric field around it. Symmetric, it's symmetric. So moving magnetic poles create electric fields, and just changing magnetic fields is another symmetry in nature. Changing magnetic fields produce electric fields. And okay, so that's the story, the interconnections. These technically these show up as interconnections what are known as Maxwell's equations, which are four relatively sophisticated vector calculus equations. You sometimes see them written on shirts of people who want to impress others. You have probably all seen them somewhere. They're a popular choice to put on a shirt as an alternative to your favorite designer. All right? In any case, they bring these observations into formal mathematical focus. But now I can show you some of these things. We've already seen some of these things in various forms, and let me just go back to them. I guess I can leave that up there. It's not bothering anybody. But let me show you one, for example, that you can produce electric fields with moving magnetic poles. And if you remember, I dragged this out ages ago. It's accumulated more dust since then, okay? This is a coil of wire. It's another one of these impossibly simple electric circuits consisting of a coil of wire and two light-emitting diodes. That's all there is. There's no battery, okay? Which means that there's no obvious source of electric power in this. What's ever going to light up the light-emitting diodes? The light-emitting diodes are arranged so that they light up when current flows. The green one lights up when the current flows one way around that loop, and the red one lights up when the current flows the other way around that loop. The name diode refers to an electrical component or electronic component that handles current only one way. It's a one-way gate for current. So these guys, light-emitting diodes, like all diodes, only conduct electricity one direction. And we'll get the green one in one case and the red one in the other. So far, so good? How am I ever going to get current to flow in this coil of wire? Well, I can do that if somehow I can get an electric field to begin pushing charges around that coil. The coil contains electric charges, lots of them. And if I can get an electric field to show up in this coil pointing in the direction of the wire, either this way or that way, either one will do, the charges will begin to move. They'll go faster and faster. The electric field will push them in the direction they're moving. It'll do work on them. They'll gather energy. They'll come out of the coil having accumulated energy per charge, also known as voltage. The voltage will go up. We'll get a voltage rise in the coil. And the coil is connected in a circuit to the light-emitting diodes and nothing else. They'll light up. Okay? And how do I make an electric field? A moving magnetic pole. It's happening, right? I can't see it. It's behind the... Okay. So I'm making an electric field. Actually, I'm making an electric field right now. It's just not doing anything interesting because there are no mobile charges in that air out there. I've got to bring in the mobile charges. There they are. They're in there. Now they're having some action going on them. Okay? And I'm actually not getting something for free in the sense that I'm clearly making electricity. Where electricity is carrying energy to LEDs, where's the energy coming from? It's actually coming from me. As I do this, I am creating an electric field which causes a current to begin flowing. That's true. And currents are magnetic. So this thing is becoming magnetic as I push the magnet in and out. And not surprisingly, the magnetic interaction between the magnetism of the coil and the magnet I'm moving is one that sucks energy out of me. Thanks. So it's taking energy out of me. Incidentally, Al sets up all these demos and stuff, so he's the real hero in this operation here. He doesn't get the credit, but he's getting the credit right now. I really appreciate it. Okay, so I'm generating electricity. It's actually coming out of me by way of the interaction between these two magnetic objects. Is that okay? So you okay with where the electricity is coming from? That I'm creating an electric field that pushes charge. And the magnetic interaction is sucking energy out of me. And I can show you, is this true? I can show you that magnetic interaction in another interesting way. So here is a magnet. This is one of these neodymium iron boron magnets. And I realized and started in talking to some of you guys in office hours that although I think there are a dime a dozen things that show up everywhere, they're all over my office, literally, as people who's visited will tell you. You haven't seen these very often. These are very strong magnets. They're a modern style of magnet. They were not available. I don't think they were had been invented when I was a kid. Two of these guys together, you get your hand pinched between them as they jump at each other, you're in trouble, okay? So it's got a tremendous magnetic field around it right now. It's got a north pole, it's got a south pole, wow, huge field around it. And when I move this around, that strong magnetic field is changing with time, or the poles are moving. Those are actually related observations. And they fit this requirement here. Moving magnetic poles, yep, or changing magnetic fields, yep, we got them both. And I'm creating electric fields. Of course, you don't see it because nothing there are no charges, no free charges to speak of that move in response to that. So some of the air atoms are going like, oh, it's funny here. There's an electric field around, but the effects are so subtle you'd never notice. But if I bring the metal nearby, currents will begin to flow. I should do this a little carefully because it's possible to go to overdo it and burn this guy up. Okay, but we're okay. So clearly stuff's happening. But instead of using a coil of wire there and having the two interact magnetically, I claimed that these two are fighting each other a little bit magnetically. They're sucking energy out of my right arm as I do this in order to generate the electricity. Let me do it with another coil of wire. It doesn't look like much of a coil, it's just a big chunk of copper. And it's a very good conducting copper, so it's high quality copper. If I create an electric field in the copper, current will flow through the copper. The current won't light any light bulbs because there are no light bulbs around, but that current will become magnetic. It'll produce its own magnetic field, which will interact with this guy's magnetic field, and they will fight each other again. That fighting of each other, that is, it will fight any movement of the magnet that creates that current. This is actually known as Lenz's law, which I haven't put up there before. There it is, Lenz's law. When a changing magnetic field, you can get it in its wording, but I want you to get a feel for the reason for it. When a changing magnetic field induces a current in a conductor, and that's what we've been doing. I've been inducing a current by playing with a magnetic field, either moving or changing. It induces a current. Underneath the word inducing is the longer story. That moving or changing magnetic field creates an electric field which causes current to flow. That's induction, okay? So it's inducing a current. The current is going to have its own magnetic field. And that magnetic field will oppose whatever you're doing to create that magnetic field. So if the magnet is approaching, before I show you the demonstration, I'll talk it to death. I know, it's a bad habit, but I do it anyway. When I push this magnet in there like that, current flows, it becomes magnetic, it fights the entry of the magnet into the coil. That sucks energy out of me, it does negative work on me, and that pays for the energy of lighting a light bulb. When I try to yank the magnet back out of the coil, it fights me again. That's Lenz's law in action. And what Lenz's law is mostly saying is that these magnetic changes always get paid for in terms of energy. The energy moves around in a way that conserves energy. Lenz's law is essentially codifying in a very oblique way conservation of energy. You're not going to be pushing the magnet in and have it suck the magnet in. It's not going to do the work for you. You got to do it. Okay? Hopefully that's somewhat followable. But now let me show you the magnetic interaction between this magnet and a coil. Well, I'm not going to use the coil because the magnetic interactions are too subtle. But they're not so subtle with this piece of copper. I'm going to drop the magnet onto the copper, which might be terrifying to somebody who knows how brittle these magnets are. Can you see how slowly the magnet drops? I can zoom in on that. Zoom in. Oops. Zoom, 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 zoom. And I can go down. We'll all get seasick here. Okay? That's good enough. All right. They're not smacking into each other at all. The problem is, as that magnet, bear in a little bit, as that magnet approaches the copper, it's a moving magnetic pole, or changing magnetic field, whatever you like. Electric field shows up, currents begin to flow in the copper, and because that copper is a solid chunk of really good copper, the currents that flow are huge, probably thousands of amperes, a vast current. And that vast current by itself has a lot of magnetism. The magnetic fields of currents are typically pretty weak, so you need a lot of them to get a strong magnet. You need a lot of current, or alternatively, you got to amplify the effect using iron, something that's relevant to the problem set into all these electromagnets. But if you can really get a huge current going, it's pretty magnetic, and that's what's going on here. Big current. And the current, in accordance with Lenz's law, the current produces a magnetic field that fights the change that creates it. In this case, it fights the approach of the magnetic field. It doesn't want that to happen. And similarly, it will fight the departure of the magnetic field, any change. So pulling this magnet off is hard. It fights both directions. In fact, it fights movement like this. This I can't show you because you can't feel what my hand is feeling. But this is hard. It's like I'm dragging something across the surface, and it's rubbing like crazy, although it's not touching. There's a huge interaction between those two. This is another demonstration of that same effect. It's just a copper pipe. Ta-da, you know, ooh, nothing up my sleeve. Okay. And again, two strong magnets. And if I simply drop these on the left and we revisit falling balls, these two magnets will hit the floor, and we can calculate it. It's some fraction of a second. It's not a full second. But if I drop them through the pipe, anyway. Pop. Okay? So these are some of the things. You're welcome to try these after class, because some of you have to feel it. Don't let this magnet jump at those magnets, though, okay? Bad juju or whatever. Okay, so that's some of the story of changing magnetic fields or moving magnetic fields produce electric fields. They really do. They drive currents around. Those currents are typically magnetic, which is interesting too. Any questions? Okay. Other things to show you with this. So I want to make sure I get to all these. Which one to do? Okay. Next one to do, if you do run current through a coil of wire, the coil of wire is actually the current itself. It's not the coil. It's the current living inside the wire that's the issue. That moving current is magnetic, and it creates a magnetic field. So a current-carrying coil of wire is magnetic, and so what does the magnetic field look like? And this is one of the questions that shows up in the homework. And it turns out that I'll try to do this approximately the way I've done it with people out of class. That is, let's unwind the coil of wire first. Pull it straight. And we have a current running to your right. In that case, the magnetic field that's produced around that current circles it. The little arrows are there. They're going around in a circle. they go around and they loop, and they end up pointing back to where they started from. And that is the structure, and where did that come from? Well, ultimately it comes from the Maxwell's equations that I alluded to earlier. So, okay, if you now take the coil and you begin winding it around a post maybe, or just wind it in the air into a big loop, those individual, the magnetic field circling each portion of wire is still there. And if you look at how all those pieces of magnetic field add up, they add up in such a way that they pass, there's a strong magnetic field going through the coil, either downward or upward, it depends on which way you run the current around that loop. There's a magnetic field heading down through the middle and then following it, returning up on the outside. And so it forms yet more sophisticated loops. If you watch the little magnetic field arrows, they go down through the coil, they come out around the coil, they continue, and they go back and loop back on themselves. So again, it's this complicated vector field of magnetic field, but it's most densely packed in the middle, inside that coil, where the space is confined. The field has to go through it. Going around the outside of the coil, it can spread out. The field can spread out, and there are various, in effect, it is not conservation, but there are reasons why once you get more room for the field to pass through, it gets weaker. So the field is strongest in the middle is the main point, in the middle of the coil of wire, and there are various demonstrations for that. But let's not go there, because actually I'm trying to go to something that's of use, both in the problem set and in just a practical world. What that means then is that if you take a chunk of iron and explore various parts of the magnetic field, you'll find that they're right in the middle of the coil. When it's carrying current, the field is strongest. It will magnetize the iron most intensely. The iron will become an electromagnet. Anywhere in this environment while current is flowing, but especially in that middle. And if you take that iron partway out of the coil, it'll still magnetize. It'll still end up with a north pole and a south pole. But one of those poles will be deeply into that central field, and one of them will be sticking out the end where the field is relatively weak. Well, if you look at the forces on those two parts of that iron piece, and let me just hold it. Here, this will be my iron piece. And it's partway in the coil. The coil's up here. And this guy's dangling out the bottom. They both will develop poles, and the poles will be in equal strength opposite. Right? One will be north, one will be south, because this has to retain its zero net pole. But this pole, being in a strong part of the field, will be pushed on harder by the magnetic field than this guy. This guy's out in nothing interesting land. So this guy gets the biggest force. And which direction is it pushed? It's pushed in the same direction that magnetized it, namely into the field, with the field. If the field is up, it will naturally develop a north pole and try to be pushed up. If the field is down, it will naturally develop a south pole and try to be pushed opposite the field up. So the pole, the part of the iron that's sticking partway into the coil will find itself pulled deeper into the coil. And this thing will go until it will find equilibrium when the two ends are equidistant from the middle. That's the special spot at which they're both pushed equally in opposite directions and they don't care anymore. So long and short, is this okay? Or questions about this? These are hand-wavy things, are always hand-wavy. The point is that a chunk of iron tends to be, it magnetizes in the presence of a magnetic field, and it tends to seek the strongest part of that field once that happens. An example of that is this. When I plug the big magnet in, I should undo this, what I've done over here. I'm here talking, and anybody watching this on the camera will never see me again. Camera home. Okay. I'm back. All right. So, you're plug this into an outlet with power. Okay. We're good. When I turn this on, which I just done, there's now current flowing in the coils. That by itself makes a magnetic field. It's moving charge after all. The magnetic field we get from that is relatively weak, so it's not very fun to show you. Instead, we magnify that field by letting it magnetize a chunk of iron, this pole piece here, or this one. The two of them are both magnetized. Actually, they're magnetized in opposite directions because the coils together are reversed. So now this is magnetized, and it shouldn't surprise you given that this is a north pole. I don't know which was which. So say this is north and this is south. The poles are right here. The field is going to be strongest right around these poles. Over here it's kind of wimpy because the two poles have sort of, their individual fields kind of cancel out here because there's some north pole there and south pole. They're almost indistinguishable. That's the strong field part, right? Anywhere around here. Therefore, this guy doesn't care right now. There's a very weak magnetic field out here. It's magnetizing, but not much. If, however, I get closer, it magnetizes more, and now it's starting to magnetize. I can feel it. And it's strong field seeking. It wants to go to a stronger and stronger field because it's being magnetized, in this case, by that pole. So if that's it, I forget what I chose. If that's south, this guy's now north. North, south, ooh, they like each other, right? And the force is getting stronger. That attraction completely dominates over the repulsion between this pole and that pole. And pretty soon, plop. Extra strong field seeking, okay? Now, once this happens, you can't get them off. And they might as well be welded in place. All right, so that's strong field seeking. I'll come back to this shortly. But I want to show you another example of strong field seeking, absolutely relevant to the problem set. I'm just getting this out of the way. And also just really important in life, not that you necessarily notice it. But here's a coil of wire. No current in it right now. I've got to turn on this power supply to make current flow in it. When I do, it will develop that magnetic field I just told you about, where the magnetic field swoops through the coil, which is, it's little, but through there, comes out the other side, swoops around, and then goes back through again. And a chunk of iron, another chunk of iron, as I claim, will be strong field seeking. It'll get sucked into the strongest part of the field. Right now, nothing. Okay, because there's just no current. So nothing's magnetic here. Once I turn on the current, and I'll do it with the little guy part way out. Ready? Get set. It's sucked into the middle. And once it's there, I can pull it out with difficulty, and it wants to go back. It magnetizes with the field and then goes to the strongest part of the field. So that's the basis of lots of electric gadgets. Before the era of let's make essentially everything an app, doorbells were not, they didn't play Rudolph the Red-Nosed Reindeer on Christmas. They would play ding dong. Do you ever encounter a doorbell that still goes ding dong? Hopefully. The ding dong doorbells, certainly of my youth, and there's, whatever. They had two bells and a piece of iron, a spring, and a coil like this. And the spring kept the piece of iron out like this. That was the equilibrium position of this, based on the spring. And when you pressed the doorbell button, you started current flowing through the coil. At which point, this guy was sucked in, and it overshot briefly. I think you probably saw the overshoot. Watch, ready? It's going to go too far out this end. Oh, prove me wrong. Got it unplugged. Yeah, it's better that than me just play games and go, this is, call 911. Okay, right. Ready? Get set. Did you see the overshoot? It's inertia, right? It got started and they couldn't stop fast enough. The overshoot in the doorbell, during the overshoot, bing, it hits the first bell. Ding. And then it goes back in the middle and it's sitting there. And it's sitting there until you release the doorbell and stop the current. When that happens, the spring returns the piece of iron which has been hovering here. The spring pulls it back to this position. But in doing so, it overshoots again. and hits the other bell. That's the dong. So when you hit the button, ding, dong. Is that okay? So if you ever encounter one of these doorbells, you can either impress your friends and family or worry them that you're getting demented by playing with it. You press it, ding, dong. Okay? You understand why that happens? All right. Okay. Other thing to go back to this, I promised that I would come back, and that is when you start the current, and right now with no current in the wires, this is an electromagnet with no current, it's nothing, it's a non-magnet. Boring, boring, boring. But when you start the current, it flows around that coil, the magnetic field begins to build up in this. It's an electromagnet. It does not become fully magnetic, the whole 9 yards, instantly. It takes time. Why? Because magnetic fields contain energy. It takes energy to magnetize this iron, and to magnetize even the space if there were no iron, create that magnetic field. The energy's got to come from somewhere. It comes from the current. The current loses energy to build that magnetic field. Well, how does energy get sucked out of the current? It gets sucked out of the current by an electric field that's created as this magnetic field is building up. Remember, changing magnetic fields are electric. And so as this magnetic field builds up, it does negative work on the current running through the wires, sucks energy out of them. And that energy doesn't disappear. It's in the magnetic field. Okay? So that's ready, get set, boom. Okay. And I could actually feel that there's about a half a second or 1 second while this piece of iron is getting sucked in. It's not instant. That's the field building up and taking energy out of the electrical circuit that's powering it. At this point, in principle, it would take no additional energy to keep the magnetic field going. The magnetic field is full of energy. Life is good. Don't have to add any more to the magnetic field. But this is still consuming electric power. Why? Because it still has to keep the current flowing through the coil, and the coil is made of conventional, ordinary metal. Copper, it's good copper, but it's not perfect. And so keeping that current flowing through wires takes energy. You've got to have a voltage drop in the wire to keep the charges moving forward by way of an electric field, and that's wasting energy, and the coils are going to get warm. I don't know if they're warm now, and I don't really want to touch them for fear that they're not perfectly insulated and I will become a light bulb. Okay, so this is full of energy. We're now wasting energy, but it's full of energy. If I deactivate the electromagnetic part, that energy is going to disappear. The magnetic energy is going to disappear, but it can't be lost to our universe. It's got to come back out somewhere. And what it'll do is, as this field begins to decay, get weaker, it's again a changing magnetic field, which creates an electric field. And now it will do positive work on the current. It will add energy to the current, whereas during the startup, it sucked energy out. Now it's going to add energy. And that energy will go somewhere. And in this particular circuit, it goes into that flaming arc here under my hand. That was the magnetic field energy coming back out. Why did it show up there? Well, it's okay. It's not worth the story, but that's the story of it. Is that okay? Any questions about this? The building up of the magnetic field, the decay, the long term, it just consumes electric power. The doorbell, same situation. When you first press the doorbell, the ding, during that part, energy is going into the magnetic field. Okay? When you hold it there to show everybody that there's no dong yet, you're wasting energy, just making heat. And when you let go, the energy comes back out. They must deal with that energy coming back out somewhere. It does not go in your hand where there's an arc under your finger. I don't know what they do with it, but it's one of those things they have to be careful about because it can destroy stuff. All right? That said, next things, agenda. Okay, this leads now, too many demonstrations, and the downside of that is what? Okay, having shown you that electromagnet, the fact that when you put energy in, initially it goes into the magnetic field and then it goes into waste, there actually are electrical conductors in the world that do not waste power. That is, there are electrical conductors through which current can coast. Essentially nothing like friction in it. The flow is perfect. And those electrical conductors are known as superconductors. They were discovered in about 1911, I believe. The first of the superconductors, Kamerlingh Onus. And shortly after he discovered liquid helium, and for good reason. The good news is superconductors exist and they can carry current perfectly, and I'm going to show them to you in a minute. The bad news is they only work at very low temperatures. How low? Well, prior to about 1990, give or take, they needed the temperatures of liquid helium or liquid hydrogen, just a hair's breadth above absolute zero. Really cold. I think the record-breaking superconductor prior to the 90s was 25 degrees Kelvin. That's 25 centigrade units or Celsius units above the real zero, absolute zero. All right. For comparison, that's about minus 240 Celsius, minus 300 Fahrenheit, something like that. Really cold. Okay. Since then, they have invented what are known as high temperature superconductors. They're still not room temperature, which would be a fabulous thing, because then electric power distribution would become wasteless. But it is possible in an ordinary class to show you superconductors because they become superconductors when cooled to liquid nitrogen temperature, which is cold, of course, and liquid nitrogen isn't completely garden variety stuff, but in a physics environment, it's pretty ordinary fare. We have it on tap in the basement. So what I want to show you is, I'll show you superconductors two ways. The idea is this, that if you've got, here, this magnet, as it approaches that chunk of copper, it causes currents to flow in the copper becomes magnetic with those currents, and it fights the approach of the magnet, right? That's Lenz's law. But if the currents, why does the magnet ever manage to land? Why does it ever get to the bottom? Well, that's because the currents don't flow for free. They eventually lose energy. They grind to a stop, and they are unable to prevent the magnet from continuing its approach. The magnet eventually touches and lands on the copper. That's a result of the finite resistance, electrical resistance of the copper. It's not a perfect conductor. If it were a perfect conductor, the currents that are created by the approaching magnet, by virtue of its electric field pushing the current, getting it going, those currents would last and last and last, and they wouldn't stop. So if you land a magnet on an ordinary conductor, or try to, it lands. If you try to land a magnet on a superconductor, it doesn't land. The currents that it creates last and last and last, in principle forever. Is that okay? Questions about that? So I'm going to look through this camera here, if I can get it right. HDMI. Okay. Get it. You are looking at a black disk. And that black disk is a superconductor. It's a superconductor, but only if it's cooled to liquid nitrogen temperature. So right now, nothing special. So here's one of these strong magnets, as you can see. It doesn't want to come off its can. So if I put this magnet down, it just lands. In fact, not only is that not a superconductor, it's kind of a crummy conductor at room temperature. But that's not the case at liquid nitrogen temperature. So it's a little bit of you got to wait for the cooling to happen. So as the liquid nitrogen boils away, it is chilling everything it's touching, including that disk. Let me just get one more. Okay, that should get the job done. So this now should be a superconductor. And when I land the magnet on it now, it's touching. Can I get it to not touch? Oops. Don't bounce. There we go. Is that good? It's trying to land, but every time it gets close, it induces currents in the superconductor, and they repel it. So this guy fall off the back. This is not obviously a stable relationship. Oh, come back. Oh, I got the two of them to close on my finger, of course. Oh, yeah, it's pretty, stop. Okay. Is it okay? So that's the first version. Let me flip this over. I don't trust myself on the inverted version. This demonstration I've never done, but Al promises me it works well. So that is a magnet suspended by induction, this induction effect, on a superconductor. These demonstrations suspend a superconductor on magnets. So they've built racetracks. This is a racetrack of magnets around here. And this is a linear racetrack of magnets. Let me get that. I want to zoom back out. Okay, so you've seen this. It's good. I can do both. How do I do this? Oh, yeah. Oh, no, I don't even have to do it. It's all good. We can keep watching like this. Great. Woo. All right. So that more liquid nitrogen here. And the container, incidentally, is basically a thermos bottle. It's a double-walled glass container with a vacuum in between. So there's no thermal contact between the inside and the outside. It's difficult for heat to flow in and boil away the nitrogen. What else? This tends to accumulate a layer of cold air above it, which also sort of buffers it against heat. It does exchange heat by thermal radiation. And in a proper thermos bottle, we would have mirrored surfaces in there to try to prevent the exchange of heat by thermal radiation. Anyhow, inside this disk, this little hockey puck, is a very thin disk. This guy, this is a broken version of the same thing. It's actually a sapphire disk with a very thin layer of superconductor on it, of this high temperature superconductor, and a gold coating. The reason for the gold coating, do I know? I don't know. Probably protection. So if we immerse this guy in liquid nitrogen, it will get cold, it will become a superconductor. Right now it's nothing special. But if we put it in, have a swim, it's now going through this transition to become a superconductor, in which case currents that are caused to flow in it by virtue of electric fields and magnetic induction, those currents will last forever. And if I put it on one of these racetracks, as I lower it, those currents will begin to flow, and they will repel. It will repel the magnets. The superconductor and the magnets don't like to approach each other, because as they do, Lenz's law tries to stop the changes that are going on. So this guy now is nice and cold. It's cold. Why? Can I get it to? There we go. The fact that it stays on the track is another effect. The superconductor allows through a little bit of the magnetic field in a way that traps it. And it gets trapped in a certain pattern of the magnetic field, and it doesn't like any changes. And so it's supported by this Lenz's law and the magnetic induction effect, and it's trapped by a more exotic effect of superconductors. So that's the racetrack, and I guess this guy will go for a long time.
So you can actually position it.
But
it should stay.
yeah. As you force it into certain positions, you're getting it to trap the magnetic field in interesting ways, and once it's done that, it sticks with that. So that's that racetrack. This is the linear racetrack, and because it's arced, it's like what is this, like a ball? It's like a ball in a bowl, rolling back and forth about the equilibrium, but it never touches.
Simple harmonic motion.
Simple harmonic motion. Yeah. Pretty cool. And it'll do that until it warms up, in which case it will lose its superconducting energy. Okay? That's pretty cool. I like that. Oh, yeah. Okay. I think I had one more thing. Oh, one more thing I wanted to show you, having burned up the whole time, which nobody. Well, no, I have more than one thing to show you, but that's life. Okay. I used to include in this class how generators work and how motors work. And just to give you a little idea, how does a motor work? Well, how does a generator work first? You've seen a generator. It's just move a magnet past a coil of wire, or move a coil of wire past a magnet. Actually, either of them will work, right? So this is a generator, really primitive. If you put some gears and some widgets around, you can make a better generator, okay? That's a generator, and I've got one here. How do you make a motor? To make a motor, use an electromagnet to attract another magnet, maybe a permanent magnet, and just as the permanent magnet gets lined up with the electromagnet, change the electromagnet, reverse its poles. So just as the north pole of this permanent magnet gets close to the south pole of the electromagnet, switch them, so that now the north pole is clear near a north pole. I hate it, and it continues. And you basically chase the permanent magnet around in a circle with electromagnets. Or you can chase an electromagnet around in a circle with permanent magnets, various choices. And actually, when you start looking at designing a motor and designing a generator, they're very much the same device. They're just, in one case, when you do work on the rotating system, it becomes a generator. And when you extract work from the rotating system, it becomes a motor. They are the same device in many, many contexts, and that's what I've got here. This is a generator. This is a motor. No, maybe this is a generator, this is a motor. They're the same. And they're wired up into one circuit. So when I turn the crank on this guy, that other one becomes the motor. And when I turn the crank on this guy, that one becomes the motor. I'm just driving the current around the circuit differently. All right? That's good enough. I still have to finish power distribution, but it was fun. All right. See you guys on Friday.